this is Chris Huckabee of Team MB1. Today I'd like to go over an overview of our system design. To begin, here is the finalized model with 5 key segments labeled. Each segment was mainly done individually by a different team member, and then we put them all together for our final design. First, the TIVA microcontroller. The TIVA microcontroller is the main brains of the operation. It is programmed to make sure the distance between the system and the steel plate was constant at all times. One of the more unique parts of our project was how we powered the system. We bypassed the USB power by affixing our power directly to the TIVA board, preventing putting stress on the USB ports and tidying up our wiring. Next, we have the power electronics. Their primary function was to control the power through the electromagnets through a PWM signal. The first part of our power electronics were the power transistors. They were used to control the power that is delivered to the electromagnets for any given PWM, but in tandem, we used sense resistors, which monitored the current going through the respective magnet and attempted to keep it constant. The next piece on our power electronics was a voltage regulator, which stepped down our 24-volt power supply from the batteries to 5 volts, which is the perfect amount to run the TIVA. As the last piece of circuitry, we have an IR sensor that feeds information directly to the TIVA whenever it receives a signal. Next up are the distance sensors. Hooked to the TIVA themselves, we have 3 IR sensors that feed in the distance between the system itself and the steel plate. As the last piece to our physical system, we have the electromagnets. We have 3 electromagnets that we could dynamically control to hover underneath any steel plate. The first part of the software I'd like to discuss is the control loop. The control loop was a feedback loop system that took in the current height and the desired height, and based on those, output adjustments to the current being delivered to the magnets, so the system would move towards the desired height, whether it would be closer or further from the plate. In addition, the TIVA was operating with a system that took in IR inputs, and based on those, edited the desired height in memory. Then it attempts to deliver a constant current through the magnets based on the height, edited by its current height. The final PWM output is either the result of this function or a constant value if the system is desiring to be in locked mode. Finally, we have a demonstration video of the system in action. The first thing that we will do is set the height of the system to its max stable level and then unlock it. Our unlocking process is slowed as to guarantee that the system will not fall if set to any stable height. As you can see from the movement, the end result is almost frictionless. Next, we increment and decrement the distance from the steel plate to show that our system is truly dynamic. We will also show that the system can be rotated around and move freely without any actual assistance from the user. And finally, our locking system is also slowed down as to prevent damage to the steel plate, the system, and making unnecessary noises. Thanks for watching.